If you're struggling to land that sweet six-figure tech job, then this video is for you. Because we're gonna show you a technical interview where you're gonna learn the skills and the strategies used to solve a problem. And make sure to stick to the end of the video because we're gonna provide you with a useful resource that will help you with your interview skills.
Hey Elijah, thanks for interviewing with OpenAI today. I'm Advay, I'm a staff engineer at OpenAI. I'm specializing in systems for ML. I'll just talk to you about how this interview is going to go. This first round is just going to be one lead code problem. Yeah, if you could just tell me a little bit about yourself, a little bit about your interests, that'd be great.
For sure. So I'm currently a senior studying computer engineering in undergrad. This summer, I interned at DoorDash. I was on the Dapper engagement team where I basically worked on a new promotion platform. So kind of writing some platform code that handles like planning out the execution of workflows for promotions. And kind of the main project that I did was adding a new type of promotion, which I will go into no further details for my NDA, but then this autumn, I was at AWS. I was on the firewall manager team, and I worked on basically a bunch of things to do with like our service quotas. So one of the things was adding like a new account limit that addresses like a scalability problem with DynamoDB, where you get like the item limit, and if you add anything else, then like writes start to fail. So I was adding a safeguard to that, and then also I integrated with some other service basically to show customers their usage.
That's great. So are you ready for the lead code problem?
Yeah, I think I am.
Okay, let's go straight to it then. Okay, Elijah, here's the problem that I have for you today. You're going to implement this function jump, which takes in an array of integers and nums. And the goal is to find out how many jumps it takes to get from the starting index to the end. At any index, you can jump up to the amount of the value of nums at that index. So for example, at the first index right here, I can jump up to 2. So I can jump either 1 step to 3, or I can jump 2 steps to this index with 1 right here. Do you have any follow-up questions?
Yeah, I have a few. So is it possible that you couldn't get to the end? Like, are we always guaranteed that you're able to get all the way to the end?
Yes.
Okay, gotcha. And then also, is it possible for it to be empty, or is that just like not defined?
You can assume that nums will always have at least one element.
Okay, gotcha. And then also, I'm just going to assume that there is nothing like wrong with jumping past the end. So for example, if we got to like the last element here and then jumped up to 4, I guess could we instead jump like 1 here and then kind of an extension question? Let's say if we were here at 3, could we jump 1 or could we jump like 1 and 2? Or 3, or is it exactly the number that you're at?
So you can jump any amount up to the number that you're at. And your goal is to get to this index. So it's not necessarily past this index, but your goal is to get to this index.
I see. And then we're trying to return the minimum number of jumps?
Yes, the minimum number of jumps it takes to get from the first index to the last index.
Okay, that makes sense to me. Yeah, so there's a few different ways that I can think to approach this. One of them is going to be basically trying every single combination of jumps from whatever our current position is. So we can look at like or starting from some index I, like let's say I is 1 right now. All that we need to do is we need to kind of recurse on the next possible jumps and try every single one of them. And so then kind of we'll be passing through this recursion the number of jumps that it takes to get to the end. So that'll be sort of the result here. And so the number of jumps from 3, and we want this to be the minimum, will be just the minimum between the number of jumps for if we jumped 1 versus if we jump 2 versus if we jump 3. And then we solve that recursively. And then for a sort of base case, we could say if I is going to be the length, then we've already gotten past, so then we would return, I think, 0 there. I guess the problem with this approach is that we'll be repeating quite a bit of work. I think that what we can do is we can probably memorize like the position and the number of jumps to get to a certain position, kind of going like bottom up. So if we started from, let's say, like index 0, that would be requesting sort of the number of jumps from the beginning all the way to the end, and then in order to compute that, we would then calculate from 2, or from 1, and then from 2. But then the key thing here is that the minimum number of jumps from, let's say, 2 here, index 2, is going to already be visited from the index 1, because it'll try and jump from index 2, 3, and 4. So we can kind of save those things since it's always going to return the minimum, and so we're never going to need to recompute those values. And then, as is the case with bottom-up dynamic programming, I think I could also probably, instead of writing this recursively, write like an iterative solution where I just use like a 1D array for each position in the array. And then I can start with like the first element there being 0, and then kind of sum up and keep track of maybe the minimum for the current position to each of like the next possible jumps. And then basically do the same recurrence relation there, but only kind of going through 2 passes of the loop, or like, yeah. So I think that you could basically just do the same algorithm but iteratively, if that makes sense. Do you have any kind of questions about that approach?
No, honestly, if you could start implementing, I want to see how you'd implement the memoization and the recursive approach first before moving on to the iterative.
Oh, okay, sounds good. So I guess I'll start actually by implementing just the iterative. I won't do memoization right off the bat, so I'm gonna start, and I'll just call this like my recurse function. And then I want to take like the position, so I'll just use index I. And then, so if I want to check my base cases first. So if my position is the last element in the list, then we've already gotten there. Is that the one that we're counting what it takes to get to here, or is it to get like one past this?
To get to exactly the last index.
Yeah, okay, so then my base case is going to be if my position is, it would be like greater than or equal to, yeah, if it's greater than or equal to the last element, or like the last position, then I'm going to return 0. And that's just because we're already here. And then also, so if we ever land on a 0, so like right here, for example, then we're never going to be able to get to the end of the list. So that's sort of another base case, is that would be like infinite jump. So I'll also say if my nums of I is equal to 0, then I can also just return max size, or I guess actually no, I'll do float of, and yeah. So I'm basically returning infinite for that, and then otherwise, so I want to keep my or I want to keep like 2 different arrays, I think. Or sorry, no. I'll keep one array, and that will be Actually, I don't think that I need any extra storage if I'm not memoizing, so never mind on that. I do want to keep track of, however, like the minimum number of jumps for this, and then also the max number of jumps that I can make currently, which is like the nums of the current position I. So I'll say like the min jumps that I've made, and that's going to be also initialized to infinity, and
Okay.
then I can just for each jump size. So for jump in, it would be from 1 to of I plus 1, I believe. Um, yeah, for each jump, and then like the next position that we're going to be at is just uh I oops I plus jump, and then I want to see, so if this is less than the length of nums, then I just need to um I need to recurse then, I believe. Yeah. So then I'll say like remaining is going to be recurse of the next position. And then if the next, yeah, if the next is equal to infinity, then this will also be impossible. So then I actually want to do, if this is not equal to infinity, then it's this might be like a candidate for a solution. So our min jump will be like the min of, and it would be itself and 1 plus the next number of, or sorry, the remaining number of jumps.
Okay. Wait, I just have a quick question. So this
Yeah.
next variable, it's storing the next index that you jump to, right? Like it's storing
Yes.
where you're
Yeah.
jumping. Could you clarify why you're checking if it's not equal to infinity? Could you explain that part one more time?
I guess actually, so I guess since this is going to be infinity, I could just do. Or wait, sorry. Can you repeat the question?
Yeah. So this next variable is storing the index that you're going to jump to, correct?
Yeah, yeah. Oh wait, yeah. No, you're so right. You're so right. It should be like the remaining. Yeah.
Oh, okay. Okay, that makes sense.
Although I think that also like this might be taken care of anyways. Wait, because min jumps starts off as infinity, and so then yeah, 1 plus the remaining. Also, I'm getting
Don't worry about that. I don't know why.
yeah.
Oh,
I
I
think
think it's because yeah, don't worry about it. It's because you're returning float info up here. Oh wait, no, it should be a float. Wait, what? Okay, don't worry about it.
uh, I think I actually don't need to check this. There is like I don't actually know off the top of my head how the comparisons with float works, or like if float or if like infinity plus 1 versus infinity is different, but I think that this is actually fine. Um, I'll come back to that though, or like this will be the first thing that I check if I'm debugging. And so yeah, after I find like the minimum jumps, then I think I just need to now return my min jump. And then in order to actually get the answer, I just need to start from the bottom and recurse my way up. So I'll start from 0. And then if I wanted to go through maybe an example with it, would you like me to do or to walk through and like trace the code? or would you prefer me to just go ahead and test it?
Let's actually do both.
Okay, sounds good. So let's say that I start with this one, and I'm going to call recursive 0. So right now I is 0. I is not greater than or equal to this. And nums of I is not 0, so neither of these go. So min jumps is in right now, and then for each jump from, and it just goes 1 and then 2. So initially my next location is going to be 1, and then if my next is less than length of nums, which it is, then I'll calculate the remaining, so it'll be the remaining of my next for 1. So I'll calculate this then recursively. Let's just pretend that it works. Take that recursive leap of faith real quick. Then the min jumps is going to be either the current min jumps, which is infinity. It's definitely not going to be that, or 1 plus the remaining. And I know that this is going to be less than infinity. So whatever the answer, 1 plus that. Would you also like me to kind of walk through the recurrence all the way through for like a branch, or do you want me to try and do it for the whole problem?
Just walk through the recurrence for this, and then
Yeah, sounds good.
just go until you get the answer, pretty much.
Okay. All right, so then right now I'm calculating the recurrence on 3, and so 3 is going to, or I'm going to check my base cases, none of them apply. The min jumps is now equal to infinity again, and then I look through next, next is going to range for all 3 of these elements. And then if next is less than the length of nums, which it will be for all 3 of these, then I'm going to calculate the recurrence for this one first, and then this one, and then this one. Let's pretend that we tried both of these and we got some suboptimal answer. And then once we got to this recurrence of 4, we then start from right there. We can check our base cases. So I is greater than or equal to the length of nums minus 1, because I is going to be 0, 1, 2, 3, 4, and the length is 5 minus 1, 4, so it's equal. So then we return 0. So now if we return 0 here, then our remaining is going to be 0 when we get off of the 3, or when we return from recursive 3. So then we compare with the min jump, whatever it was before, versus 1 plus 0, and then that will give us 1 for the answer to 3, and then once we go back to 2, so our remaining for 3 would have been 1, and then we compare that with the original flow of infinity, and then 1 plus the remainder, which is 2. So then the answer is going to be 2.
Perfect. And could you just write
Right.
a quick test case? Don't worry too much about using assert or whatever. Just prove that. We'll actually run it.
Yeah.
Just prove that for the input.
Am I able to run it? Oh, okay.
I think you are.
Incredible. No error.
Perfect.
Maybe one thing that I would like to try is if I did like a, or no. Let's say that I had a 0 and a 0. Because I know you said that this isn't a case that could happen, but I expect this to return infinity.
Okay.
Yeah, okay, cool, it does. Sorry, I interrupted you there for a sec.
No, so I was just going to ask, when you were describing your approach, you mentioned 2 optimizations. One was memoization, and the other one was an iterative approach with dynamic programming. Could you just, I guess, implement both of those? And you don't have to walk through you don't have to walk through the memo approach. But once you implement dynamic programming, I think I'd like to see you walk through that.
That sounds good. So I'm just really quickly memoizing the min jump. And so then theoretically this should still work. Although, let's see, for my base cases, I can actually just evaluate this directly. I don't feel like adding them to memo. So if I run it again, looks like that passes. Just saving each thing so I don't recompute any answers. And then for the iterative solution, so my
Actually,
idea
wait.
here is, oh, sorry,
Yeah,
go
stop you
ahead.
right there. I forgot to mention this, but could you state the time and space complexity before and after memoization?
Yeah, I can certainly try and do that. So before memoization, we're basically trying every, let's see. Yeah, so we're basically trying every like possible jump that we could do. And so then if we go over like all n of the numbers as like starting points, and then potentially try up to like all n other numbers, or like basically n jumps, then I think that that would be like an n squared approach. Does that make sense? And then the space complexity would be, let's see, it would also be n for like the stack space, I believe. Could be wrong though. And then or wait, do you wanna say whether or not that's good, or
Say one more time how you evaluated the time complexity before memo.
yeah, so before memo, here's my thinking. I'm not gonna pull out the master's theorem for this. So if we have like I candidate starting points, or sorry, n for each of the I, then we kind of have like n different things that we could compute. Um, and then yeah, so we have like loop over n starting points. And then inside of each of those starting points, we potentially are going, like, we're going to jump a minimum of one time. So in the worst case, if like all of our jumps are just one, then we're only going to jump, oh, actually, now that I think about it, we're doing kind of even more repeated computation because we might jump once, we might jump twice, and so on. But we'll recompute each and every one of those. So then maybe like a different worst case is if all of them are like n, or all of the values are n, then I think that actually, let's see, we would do, starting from even just like one, we would go over two, and then three, and then four, and then five, and so on. But then each of these, like two would then be triggered, and that would try three, four, five, and so on. And then three would also try, uh, oops,
Mm-hmm.
and so on. So maybe this is actually going to be factorial, perhaps. Could be
Close.
wrong on that.
Think about, if it helps, think about how many recursive calls you're making
Oh
per
wait,
index.
yeah. That makes sense. Yeah, so we're making n recursive calls, so there actually be n to the n, I believe.
Yeah.
In the worst case, where like each value is one or is n. Okay, yeah, that makes more sense. I was honestly just guessing both times. It's been a minute.
You got there. You got there.
All
Okay.
right.
What about after memo? Let's just do time complexity after memo.
All right, after memo, instead of recomputing each of these, so if we start with like one, then we are going to also calculate two, three, four, and so on. But we're only doing each of those once, and then like in the subcalls, basically each one is going to compute like its neighbor, and so we only visit each of these positions once, so it'll just be O of n.
Cool. That's what I was looking for. All right, we still have some time left. Do you think you can implement your iterative solution?
Yeah, I can certainly try. So wait, I want to keep my test cases. So I think the main thing here, I guess I could still use a dict if I really wanted to, but I know, and I could have done this for the memoized one too, but it's just a little bit more natural for me to use an array here. So I'll initialize like an array of all infinity, and then this will be n long. Or actually, I guess maybe a cleaner way of doing this. And then I want to set like my base case explicitly here. So I'll also have memo of 0 is going to be equal to 0. And that is sort of like a backwards way of thinking about it, but we're actually going to go or actually, let me think about the best way to convert this code. I shouldn't have deleted my iterative or my what do you
Hey,
call it?
you can
My
bring it back.
recursive stuff.
Yeah,
I don't think necessarily need it.
All right.
So I think yeah, I think instead of or we can start with 0 and then like we can still start from the bottom, but basically just keep like a running um a running like sum while we're going. So for like each position, or like we would keep like the I in range, and we're gonna iterate over just each number this time. So for each I, then we want to get like the basically the maximum, yeah, the maximum like distance that you can jump from like the current position. So that would be, I guess we have uh two options there. One of them is, I think if we are gonna jump like further than the bounds, like we don't want them to say that the position goes like past the end of num. So we can keep it like less than or equal to the length. And so we can say like the max distance is going to be the minimum between, so it can just never go over the length of nums. And let's say the current position um, plus the number that we can jump from the current position. Does that this sort of make sense?
Yeah, I get that.
Okay, cool. And so then we can also have like this sort of for the next position, the next, and this will be from the current position plus 1, because we jump at least 1, and then to the maximum distance, I think. Yeah. Maybe I think this should actually be stated as like max position would be a more apt name for it. Then we want to calculate, so what is the minimum number of jumps that we can get for this next position? And so that will be in our memo. We'll want to set this value. And this is where like the main recurrence relation happens. So we have two options, and we want to pick like the better of the two. So we'll use min. And then we want to do it's either going to be already computed, which is just like memo of next. And if this isn't already computed, it's going to default to infinity anyways, so it's not a big deal. It's either that or it's going to be like choosing the jump from the current position. So we could also have like 1 plus memo of I. So it's sort of simulating like if we had jump. And then I think now that we're that we've sort of gone through each of these and built up our memo, basically what we want to know is we want to know the last value, because that will store like the minimum amount that it took to jump to this position. So then if I run, or actually, do you want me to first go through a test case instead of just running it?
No, let's just run it. Let's see.
Oh no, I have an assertion error. Let's see if I can debug it really quick. So, and then this should definitely start as 0 because it takes 0 jumps to get to the 0th position. And then, let's see, I is my current position. And then, so the max position being the minimum between length and versus I plus nums of I. Oh, you know what? I think that this should actually be I plus nums of I plus 1 perhaps? Or wait, should it be?
What's your reasoning behind that?
I'm trying to think. Wait, so if we start from I and that's like 0, and then plus nums of I, so this would be like to 2, then we could only jump from this one to the, or I guess no, that does actually, that makes sense. Oh, I think actually it would be like a plus 1 maybe here, because this is what do you call it? This is exclusive, but then yeah, it's so I was thinking that this should be max position plus 1, because if max position is a valid position, so then I can just do -1 here. I think would fix it. Yeah.
Okay, let's run the test cases one more time. There we go.
Oh yeah, okay, that fixed it.
Okay. Now actually, yeah, let's do time and space complexity of this
Okay,
approach.
so space complexity is just this n, and then I think it's also pretty clear to see that the space complexity, or sorry, the time complexity of this is going to have an n right here, and then the next range thing, I suppose actually, I think in the worst case this could be n squared. I'm not, like, I guess it depends on the values, but like for this example, we're going over all n characters for time, and then we're also like jumping ahead, but we're not really saving on any computation here, because we are going through like each next position, if that makes sense.
Yeah.
But then in the worst case, our values here would be they would be like n, so then it could go up to n squared. I feel like
Well, why do you think it's not n squared?
mm, because I think that yeah, it makes sense that it would be n squared. I think the thing that I'm having trouble wrapping my head around is that I originally thought that the MemOI solution was n, and I was thinking, how could this be worse? But now that I'm realizing that we're still doing n calls for each of the n like numbers in the list, where just each one of those n calls is going to be constant time. So yeah, no, it makes sense that it would be n squared as well. That was the only source of doubt, though.
Cool. Okay, Elijah, that was a good interview. Thanks for taking the time to interview with OpenAI today. We really appreciate it. Um, we'll have your results on whether or not you moved on to the next round in about 4 to 5 business days. Yeah, thanks.
If you want to improve your interview skills, then check out the website in the description below. And thank you guys so much for watching.